Hello and welcome to Self-Defending Borders, a developer's approach to security, part of the AWS Innovate online conference. In today's modern world, your border is an interface between yourself and the consumer. Businesses today not only need an online presence, but need to ensure they can deal with an ever-increasing hostile environment. But is traditional security enough, given that modern-day attacks focus at the application layer? In this session, I will illustrate how you can leverage AWS development services in conjunction with traditional security services to create an architecture that dynamically responds to what is occurring in your environment, allowing you to build a self-defending border to protect your online assets. Just a bit of level setting for today's session. We're going to spend about 30 minutes together exploring a use case of how you can use development services to transform your edge from one that is static, which forces you to play cat and mouse, to one that is proactive, self-defends and drives maturity in your security practices. For many of you, the services and concepts discussed here will be quite new, so I'm going to walk you through a few demonstrations to illustrate the art of the possible, focusing in on how development services can augment and add value to your security posture. And because we're all builders, there'll be no black boxes in this session. I will demystify the underlying reference architecture and implementation details behind these demos. We only have 30 minutes, so let's get started. Let's talk about the state of play in business today. In this ever-changing digital world, the frequency of attacks are increasing year on year, and at the same time the attack vectors are becoming more and more complex. Businesses are often extending the life cycle of their security investments, prolonging and sweating their assets. There is an ever-increasing amount of rules and regulations for compliance that need to be adhered to, and let's be honest, it can be a struggle to be compliant. And lastly, we have a plethora of isolated systems and log sources that we struggle to extract value from. So what are the threats facing today's online assets? Well, there are many, so let's talk about them. Whilst there are many attack vectors, attacks are shifting towards the application layer. And at the application layer, we have the Open Web Application Security Project, or OWASP for short. The OWASP Top 10 is a list of the 10 most dangerous current web application security flaws, along with effective methods for mitigation. We're talking here attacks on web applications via methods such as SQL injection, insecure deserialization, cross-site request forgery, and so on. The OWASP Top 10 was last updated in 2017, and it's no surprise that number one on the list is injection. Almost any source of data can be an injection vector. Injection flaws occur when an attacker can send hostile data to an interpreter. Injection flaws are very prevalent, particularly in legacy code, and are often found in SQL and NoSQL queries, LDAP, as well as XML parsers and SMTP. Whilst injection flaws are easy to discover when examining code, injection can result in data loss, corruption, disclosure to unauthorized parties, or denial of access. In some cases, injection can lead to complete host takeover. Pretty serious stuff we should be mitigating against. Let's take a look at this simplistic example. I've decided to log in to a website and have entered in my username and password. This has translated into a SQL query from the web application to the database engine, and it might look something like this. Pretty innocent. But we know not everyone is innocent, and by not validating our user input, our malicious actor is able to modify the SQL query being sent to the database engine, and in this scenario, all usernames and passwords would have been returned as a record set. Obviously, the query would require a bit of massaging to return as HTML output, but you get the gist. So how does a typical business tackle these threats today? We use controls. And we have various controls in our toolbox to provide countermeasures. But there are problems. The traditional approaches of defending one's border doesn't scale in terms of effort versus return. Firstly, these proprietary systems and appliances are often expensive, attracting high capex startup costs, while requiring professional services for implementation. Equally as important, IT departments the world over are adopting a DevOps model. These departments rely on automated deployments and often see an opportunity to automate their security operations, DevSecOps. And these security systems often lack multi-vendor integration. Lastly, if your site has a high release cadence, how often is your security getting in the way of genuine transactions? So enough theory here, let's see this in action. Let's look at this problem through the lens of our fictitious website, the Snowy Unicorn Elevator Company. Their website is based on the popular commercial off-the-shelf software WordPress and has been modified to work with their ERP and CRM platforms. They have just invented a revolutionary new type of elevator that has thrust them into the digital era. Traffic to their website is growing by orders of magnitude month on month. But because of this invention, they are growing quickly, and with IT not being their core business function, the security posture at the snowy unicorn elevator company could be described as block and tackle at best. They lack operational intelligence. They are reactive, making manual firewall changes, do nothing with their log artifacts, and recently received a ransom email stating that their website would be DDoSed unless they transfer 50 bitcoins to a Bitcoin wallet. I hope none of this sounds familiar. Before we switch into our demo, I'd like to talk about their architecture. Starting from left to right, their users resolve their website via Route 53. The website resolves to an application load balancer, and to ensure deployed capacity meets user demand, they have implemented their front-end servers in an auto-scaling group. On the back end, they are using an RDS MySQL DB configured for high availability across multiple availability zones. They also have a Bastion host in their front end used for remote administration. But we also have bad actors. And whilst we can lock down known ports to known IPs, being an online business, they need to keep 443 and 80 open to everyone, including bad actors. What will they do? Today, I'll be using Kali Linux as it will form the basis of our attacks. For those who aren't familiar with Kali, it's a Debian-derived Linux distribution designed for digital forensics and penetration testing. It contains hundreds of pre-installed tools perfect for prodding and poking systems. It's available for 32-bit, 64-bit and ARM systems and is available in the AWS Marketplace. Wearing my attacker's hat, what attacks will I be performing? Let's quickly talk about them. Firstly, I need to do a little bit of discovery to understand what I'm working with. What I'm looking for here are breadcrumbs of information that will help me plan my attack. HTTP headers, script engine versions, directory structures, and so on. I am next going to extract as much information as I can, perhaps for a future phishing campaign on their customers, before launching some OWASP-style attacks. I'll add a serving of denial of service, and the cherry on top, a brute force attack. Let's switch to a demo. Let's start off by viewing the Snowy Unicorn Elevator Company's website. As per our recent topology diagram, it's a two-tier website running Apache on the front end with MySQL on the back end. Pretty standard stuff here, and given WordPress powers 29% of websites worldwide, it should have synergies to the websites many of you manage and keep secure today. Wearing my attacker's hat, I'm going to launch our attacks. In order to complete a future phishing campaign, I'll need a copy of their website. So let's see if we can spider and scrape this site. I have 3 SSH sessions open to the same Kali Linux instance, and I'm quickly going to open my shell script, which is using a combination of curl and wget to scrape their website. Whilst it's executing, let's take a look at their robots file. And based on the robots file, assuming I didn't know this was WordPress, showing /wp-admin is a pretty clear indicator that this is WordPress. Even if I wasn't familiar with WordPress, I can quickly validate this with a search engine. Given I believe this is WordPress, let's use Kali and perform a scan of this site with the WordPress vulnerability scanner, WP-Scan. WP-Scan can take some time to run, and given we are time limited, I've run this just before the session. Let's take a look at the output. And based on the output, I can deduce the following. The version of PHP is 7.016. They are behind on patching WordPress, not too far behind, but the build is from January. There is a vulnerability with versions of WordPress less than 4.94. which by happens to be the current version of WordPress. And lastly, a theme and plugin have been applied. The plugin that WP-Scan detected is called Apartment Management. And Apartment Management is a WordPress plugin that is designed to manage housing, society, and neighborhood maintenance tasks. The Snowy Unicorn Elevator Company has altered this to manage not houses, but maintenance tasks of their elevators. One of the many functions of this plugin is the ability of users to send messages to each other or groups. Now, I've done some research on the internet and prodding and probing against this plugin, and whilst WP-Scan doesn't think it's vulnerable, I do. I've crafted some pretty interesting URLs to perform a SQL injection. Shall we try these? Let's look in our IDE at our SQL query. And as we can see, this is T-SQL, but we are having to use HTML separators and craft a T-SQL in a manner so rather than returning a huge multi-row record set, it returns as one record set. And it's also not as simple as just sending this to the MySQL database engine. We need to encode it, and it will look something like this. So I just ran this, and by modifying a query string and encoding a select statement, what I've been able to do here is list all the tables in their database. One table stands out, and it's the accounts table, as it does not have the same WP underscore prefix like the other tables. Let's look at what fields are in this table, and we can deem this by looking at the information schema. And now, since we know the table names, let's dump out the data. We now have some pretty juicy personal information here. We now have first and last names as well as their date of birth. WP Scan stated earlier that there was a vulnerability in all WordPress versions. And after reading about this, I've crafted a Python script to exploit this. What this script is going to do is for every HTTP post, cause Apache to generate approximately a 4 megabyte payload. Even if I can't bring their website offline, I can at the very least cause them financial pain by increasing their outbound bandwidth by hundreds of megabits per second. And in order to amplify this attack, I'm going to run this from multiple SSH sessions. Let's check the website, and what I hope will happen is the website is going to go slow, come to a crawl before Apache finally gets exhausted of resources and crashes. There is a bastion host in this architecture, and whilst it's not possible to query a public zone for an A record, an Nmap subnet scan with TCP/IP fingerprinting will clearly show some information about the host. And in the wild west of the internet, such scans occur with high frequency. In running Nmap, we can see that 3389 is open, which is RDP. And for good measure, I'm going to try and force my way in using a dictionary attack using the brute force tool, Hydra. I'm going to assume the standard Windows Administrator username and iterate through a password list of 2.1 million passwords. Let's leave this running and switch back to the slides. So, what did you think of the website? All the trademarks of an expert UI design team, right? Look, for a company relying on its digital presence, one guy with a laptop in 10 minutes has caused chaos. Their defense was inadequate. Their website is currently down. They can't do business and they can't manage their inventory. Personal information was just exposed, and with the increase in data breach notification laws around the world, this could have very serious consequences for the Snowy Unicorn Elevator Company. This could be the end for them. But what's scary is this all flew under the radar. I didn't invite you here today to focus on building a better candle. I want to focus on building a light bulb. Self-defending borders. We have a new architecture, and let's talk through our architecture before we jump into some more demos. At the core of our self-defending architecture is AWS WAF, and more specifically, the Web ACL, that acts as a central inspection and decision point for all incoming requests. The protective functions of this architecture will determine the custom rules that are dynamically injected and removed from the Web ACL. Our domain is resolving to a CloudFront distribution, which is protected by AWS Shield to only allow HTTPS requests to make their way through to CloudFront. CloudFront is handling both static and dynamic requests, and for those requests that can't be performed at the edge, CloudFront will retrieve from the origin, which is our application load balancer, and this is set to only accept requests from CloudFront, which is further reducing our surface attack area by preventing requests directly accessing the origin. Just as the saying goes, if you're not keeping score, well, it's just practice. Without logging, it's virtually impossible to detect our malicious actors. All logs generated by CloudFront, the ALB, and the web servers, Apache, are being pushed into an Amazon S3 bucket, which will be ingested by our architecture to drive operational intelligence. Lastly, we have our honeypot endpoint, which is a security mechanism intended to lure and deflect an attempted attack. I chose WordPress today because, other than being popular, there is a lot of collateral that is easily available online on how to compromise an unpatched, unsupported WordPress website. The honeypot detects inbound requests from content scrapers and bad bots that don't obey a robots file, and to catch those who are trying to access known application exploits. If a source accesses the honeypot, we will kick off an appropriate workflow. Let's drop back to a demo. This time we have a new website URL, selfdefending.tsuec.com. We have the same content and same robots file, and other than a different fully qualified domain name, it's the same website. But don't take my word. Let's look at the results of WP Scan, to which I also ran earlier. And to make it clearer, let's drop to an IDE and diff the results between our self-defending architecture and our original architecture. Still WordPress 4.79. Still one theme and a plugin. I hope you can now see there isn't any smoke and mirrors going on. But did you notice anything else in the output? We now have CloudFront and Shield Standard sitting in front. I'm going to now try and execute the same SQL injection. The application is still vulnerable, but the OWASP rules within our web ACL have decoded my request, identified that this is an injection, and blocked it. Before, I was able to extract personal information including first and last names. They have gone from having a terrible day to being able to block, receive notification, and take programmatic action. Whilst I can't run my SQL injection, I still should be able to render their website offline. Let's drop back to Kali and use our Python script. The requests are now racking up, but the website is still up, and it is actually quite performant. And we can quantify the response times with Firefox Inspector. And as we can see, the site is not only online, but still performs very well. And this is because Shield Standard and CloudFront are dropping these requests at the edge, with requests never making their way through to the origin. I'm going to pause in our architecture here and change gear, because not only does AWS provide you a suite of best-of-breed security services, but you have a portfolio of building blocks to help you architect and develop robust security practices. And as builders, these are the building blocks we're going to use. You have SQS and SNS, our managed queuing and notification services, to help decouple and provide reliable messaging. There's DynamoDB and S3, which provide durable and scalable storage options for logging and audit trails. As you can see, I've listed quite a few non-security services. And that's because in 2018, security can't be looked at in isolation. And it's these services that really empower you to build modern security architectures. The key to adding smarts into our border is the use of AWS Step Functions and AWS Lambda. These two services are adding enterprise rigor and robustness, giving us a capability to dynamically drive configuration of AWS WAF and other applications based on site behavior. Let's quickly refresh our understanding of Lambda and Step Functions. AWS Lambda is a serverless compute service that runs your code in response to events, such as HTTP requests via Amazon API Gateway, creation of objects in Amazon S3, state transitions in AWS Step Functions, and so on. The code you run on Lambda is called a Lambda function. After you create your Lambda function, it's always ready to run as soon as it's triggered. Serverless means having a simple but usable primitive. Your code as a Lambda function with nothing that looks like a server or a container. There's no need to worry about provisioning, securing, and configuring servers. No more Patch Tuesday. Availability and scalability is managed by us, and unlike your on-premises, EC2, or container deployments, you never pay for idle time. You only pay for compute time. That is the time your function takes to run in units of 100 milliseconds. And that is why Lambda is perfect for our honeypot event-driven architecture. Equally as important is AWS Step Functions. AWS Step Functions is part of the AWS serverless platform, and it makes it simple to orchestrate Lambda functions for serverless applications. If you're using Lambda today, I bet there aren't many apps with only one function, one entry point, one module, one component. In fact, it's common to have lots of functions, and this is where Step Functions comes in. Step Functions is a reliable way to coordinate the components and step through the functions of your application. Step Functions automatically triggers and tracks each step, so your application executes in the order as expected. And if things do go wrong, you can diagnose and debug problems quickly. So why Step Functions? For us today, it's adding robustness and gates to business-critical workflows to avoid false positives. You use the JSON-based Amazon States language to write your state machine. As you construct your JSON, it will be visualized in the console. You define your workflow as a series of steps and transitions between each step. When you start a state machine, you pass it input in the form of JSON, and each state changes or adds to this JSON blob as output, which becomes the input to the next state. Today, I'm using step functions as a common pattern, but let's talk through this specific case with our honeypot. Our step function is being invoked with a payload of JSON data, and it will start via a call originating from an API gateway when our WordPress honeypot is hit. Our Lambda function intercepts and inspects the request headers to extract the IP address and the HTTP user agent of the source that accessed the trap endpoint. Our state machine logic evaluates the HTTP user agent to deem if we have seen this attack vector before, and it does this by looking at a DynamoDB table. If there is a user agent match, we add the IP address to the AWS WAF. Otherwise, we progress in our step function to the manual approval Lambda function and send an email to an InfoSec team requiring human intervention. And if our InfoSec team deem this to be a malicious HTTP user agent, the approval response and step function task token will flow back through Amazon API Gateway, and the HTTP user agent will be added to the DynamoDB table and the IP address that hit the honeypot to the WAF ACL. What I have built here is a reusable and extendable pattern that will be used throughout our self-defending architecture. If you want to learn more about this manual approval process, I'll leave links to this in the session summary. I just mentioned the ability to notify our InfoSec team. In order to decouple our architecture and provide a mechanism for messaging to our InfoSec team, I'm using Amazon Simple Notification Service. Amazon Simple Notification Service is a flexible, fully managed pub/sub messaging and mobile notification service for coordinating the delivery of messages to subscribing endpoints and clients. Messages can be delivered over multiple transports, such as Amazon SQS queues, HTTP endpoints, Lambda functions, mobile push messaging, SMS, and email. SNS has a simple API allowing you to create topics, add subscribers, and publish quickly and easily. And finally, being a higher order service, SNS is reliable, with messages stored across multiple AZs. Let's drop back to a demo. We are back in our Kali Linux session, and we're using the same shell script to scrape. This time the target is our self-defending architecture. Switching back to our robots file, we can see we have a few directories that compliant spiders and indexes should stay clear of. But the thing is, being a scraper, I don't care, and my script isn't compliant. Let's execute this shell script. The shell script is running, and my phone in my pocket has just started vibrating. I'm sure I received a message, and rather than looking at my phone, let's drop to my email and read this in full. The honeypot was hit by my scraping script, and we can validate this by looking at the wget output. API Gateway is configured as a proxy pass-through to our Lambda function, which is returning our message, "Thanks for visiting 54.252.156.11," which is the IP address of our Kali Linux instance. If I drop into the step functions console, we can see we have an active state machine. Our step function was invoked with a payload of JSON data. And based on the state machine logic, we are in a manual approval process. I'm going to drop back to my email and click approve. This will flow back through API Gateway, which will pass the state machine task token and approval result back as input for the next step, which will execute a Lambda function, update WAF badbot ACL, which will then update the AWS WAF. We can validate this in the AWS WAF console, CLI, or SDK. As you can see, I'm in the WAF console, or we can use our script again, which is now returning 404s. A development principle is to always use feedback loops, and that is how I like to think of this last function, as a safety net should our previous attempts not be successful. I've added another AWS service to our solution, AWS GuardDuty. GuardDuty is a managed threat detection service that continuously monitors for malicious or unauthorized behavior to help you protect your AWS account and workloads. It monitors for activities such as unusual API calls and detects potentially compromised instances or reconnaissance attempts being performed by malicious actors. So what value is GuardDuty adding to our border? GuardDuty is providing our step function, the IPs of those who are managing to hit our environment with unusual access patterns, as well as IPs from third-party IP reputation lists from Spamhaus, Proofpoint, and the Tor exit node list. These findings are delivered as a JSON payload, to which we can use to feed our step functions Lambda pattern to provide logic evaluation and branching before manipulating AWS services. In order to generate findings, GuardDuty leverages 3 different data feeds. It firstly evaluates a duplicate VPC log stream that we operate, so there's no need to turn on VPC flow logs. On the DNS front, it monitors queries made from EC2 instances to known questionable domains, as well as Route 53 logs if you're using Route 53. Then lastly, your CloudTrail history of AWS API calls used to access the management console, SDKs, and CLI, plus the identification of the user account and source IP, making the call feed into GuardDuty. All of this data is then used to generate findings. GuardDuty findings are made available via CloudWatch, so not only can you detect, but you can report and act. From CloudWatch, you can leverage CloudWatch events to act on this information via services such as step functions and Lambda. Or you could use Amazon Simple Notification Service to send this information to a SIEM or SOC. With such rich integration, the choice is really up to you. Let's drop back into a demo. In the very first demo, I launched a brute force attack using Hydra. In fact, it's still running. And while speaking a few minutes earlier, my phone vibrated again. I bet I received another alert, but rather than look at my phone, let's drop to my email. GuardDuty has detected this brute force attack via our duplicate VPC log stream, and we are using the same step functions pattern to take action on these findings. Let's take a look at our state machine. And this time, when we click approve, rather than updating AWS WAF, our Lambda function is updating the EC2 guest OS firewall. And before we do this, let's check to validate we can telnet to port 3389. And we can. So let's hit approve, and again, this should flow through API Gateway into step functions and via Lambda into the Windows firewall of this instance. Now let's see if we can telnet to 3389. And just like that, we have leveraged a GuardDuty finding to trigger an orchestration within our environment. Let's recap what we just saw. We climbed the curve. We took the Snowy Unicorn Elevator Company from an architecture that was static and provided little to no visibility to one that is self-defending. And we did this not only by utilizing traditional security services, but by looking through the AWS toolbox and combining security services with those you see above. Services that were once the realm of developers and architects have augmented our architecture, providing us a pattern that will scale for other attack vectors, whilst at the same time we did this in a way that will reduce our operational overhead. You're probably thinking, can I afford this, and what does something like this cost to run? Let's find out. Just under $20 per month. That's less than the cost of a movie ticket. So what does $20 buy us? Just a disclaimer, all prices are accurate as of today, and prices are in US dollars for the Sydney region. Obviously, each and every environment is going to be unique, but let's use some rough arbitrary figures. Let's assume my website received 10 million HTTP requests, generating 1 terabyte of outbound traffic. Our architecture today used one web ACL with 5 rules, which is the bulk of our cost. API Gateway was used for our honeypot and manual approval process. And unless you're getting hit a lot, this is only going to cost a few cents at best. Which could also be said for Lambda. Whilst it's the glue for our step functions and API Gateway requests, it costs 20 cents per million requests. GuardDuty has to be turned on at the AWS region level. And today it's picking up findings not only for this architecture, but for everything else running within my AWS account. But what we typically see is GuardDuty costs typically equate to less than 1% of a customer's total AWS monthly spend. And my favorite AWS service, step functions. Whilst being the workhorse in this architecture, step functions is only costing a cool 10 cents. And lastly, Shield Standard is completely free. And what I didn't mention is the fact that most of these services provide a free tier. So depending on your usage, you may find this architecture is free or almost free. In summary of this session, security doesn't need to be static. The AWS platform isn't, so why should your architecture? Leverage the portfolio of AWS development services in conjunction with the rich programmatic AWS platform to drive maturity in your InfoSec practice, allowing you to build a security architecture that automatically responds to the dynamic threats you face. Cloud security at AWS is the highest priority. The AWS cloud provides you with a platform to scale and innovate whilst maintaining a secure environment. And lastly, traditionally, security has been expensive to implement and maintain. It doesn't need to be. Many of the features we saw here today are either free or are almost free, and the full feature API integration allows for quick and timely implementations, allowing you to quickly de-risk your business. Please see the following links to get you started with AWS Lambda and AWS Step Functions, as well as links to the AWS WAF automation and Step Functions manual approval workflow to which we have seen today. To gain more confidence and hands-on experience with AWS, access the digital training built and delivered by AWS experts. AWS has a wide partner ecosystem to help you focus on your success and take full advantage of all the business benefits that AWS has to offer. To learn more about how APN partners can help you, visit the AWS APN booth at our showcase. Finally, I would like to thank you for attending today and sticking out until the very end of this presentation. I want to wish you good luck in transforming your edge to one that is self-defending.